Okay, in this video I'm going to be talking about elimination methods for solving systems of linear equations, in particular Gaussian elimination and Gauss-Jordan elimination. So when I did my video introducing matrix methods for solving systems of linear equations, we talked about common approaches to solving the ax equal b problem. So ax equal to b. This is the classic problem in systems of linear equations. So if I multiplied this matrix equation out, I would actually get three equations with three unknowns, x1, x2, and x3. And so they've been put in matrix form, and now we're going to use matrix techniques to solve this problem, or to find a solution such that we can have numbers associated with x1, x2, and x3 that satisfy these three equations. So the class of methods known as elimination methods are a very common and powerful set of methods used to solve ax equal b problems. And I'm going to demo Gaussian elimination, and Gauss-Jordan elimination here. So here I have a matrix and a b vector, so a coefficient matrix here, and my b vector here. And when I do Gaussian elimination, or any kind of elimination, at least by hand, a common way to do this is to augment the a coefficient matrix with the constant b vector. So I'm going to do that over here. So I'm going to write my A matrix, which is 1, 1, 1, 2, 3, 7, and 1, 3, minus 2. I'm going to put a little dotted line here to show that I'm augmenting this matrix with this vector. I'm going to put the b vector over here, 3, 0, 17. Okay, I'm going to make this look like one big matrix. Now, the general idea in elimination methods is to eliminate unknowns. So elimination is the name that these methods get because they try to eliminate unknowns. So let's see here, eliminate unknowns. Alright, so if I had these three equations and I actually had them in equation form, it might look like this. So I have, for the first row, this row right here, that equation corresponds to x1 plus x2 plus x3 equals 3. The second equation is 2x1 plus 3x2 plus 7x3 is equal to 0. Now if I have these two equations, I can combine them to eliminate one of the unknowns. So I could multiply this entire equation right here. I can multiply it by minus 2 and then add it to this equation right here. And if I did that, what I'm going to get is minus 2x1 plus 2x1 is going to be 0 times x1. Now this is minus 2x2 plus 3x2 gives plus x2. And then minus 2x3 plus 7x3 is 5x3. And then minus 2 times 3 is minus 6. Plus 0 equals minus 6. So I get this new equation where I've now eliminated one of the unknowns, and now there's only two unknowns in the equation, x2 and x3. So I can do a similar process to this augmented matrix up here by multiplying this row by minus 2. So multiply this row right here that I'm underlining by minus 2 and adding it to the second row right here to introduce a 0 in this place. Okay? And I can do that. It's just the same thing as what I'm doing here when I'm multiplying one equation by a constant and adding it to another equation. It doesn't change the equations any. All it does is eliminate some of the unknowns. So in elimination methods, what we typically want to do is we want to eliminate enough unknowns that we can solve the problem. So in Gaussian elimination, we try to eliminate all the coefficients in the lower diagonal portion of the matrix. So this is the main diagonal right here, 1, 3, minus 2. Is that minus 2? Yeah, minus 2. That's pretty poorly written too. So minus 2 here. Okay? And we want to introduce zeros at these locations, 2, 1, and minus 3 that I've circled here. So let's go ahead and do that process just so you can see it. And let's rewrite this, I guess, over here. So let's grab this and put it right here. So I'm going to have 1, 1, 1, 3, minus 2, 3, 7, 0, 1, 3, minus 2, 17. Alright, so if I multiply this first row by minus 2 by plus 2, this shouldn't be minus 2. Let's see here. Let me just erase that real quick. Alright, there we go. Not minus 2, plus 2. Alright. And add it to the second row. What we're going to get is a new set of equations here that obey the same constraints. So I'm still going to have 1, 1, 1, 3. And now I'm going to have 0, 3. Let's see, make sure I know 0, 1, 5, and minus 6. Right? Now this equation on the bottom is still unchanged. 1, 3, minus 2, 17. But now I have a 0 here. So now if I want to introduce a 0 at this location right here, I can multiply this top row by minus 1 and add it to the bottom row. And now if I do that, I'm just going to write the result over here. I'm going to have 1, 1, 1, 3, 0, 1, 5, minus 6. I'm going to have 0, 2, minus 3, and then minus 3 plus 17 is going to be 14, right? So 14. Alright, now I've introduced zeros in these two locations. I just need to add a 0 here. So I could try by multiplying this first row by something and adding it to the bottom row, but the problem is this first row has a 1 here in this first slot. So when I do that, it's going to put something where this 0 is and wreck our work. So I can still do the same thing by multiplying this second row by some constant and adding it to the last row, and then because this second row has a 0 here, it's not going to disrupt our work. So if I multiply this second row by minus 2 and then add it to the third row, then I should introduce a 0 here. So if I do that, here again I'm going to have 1, 1, 1, 3, and 0, 1, 5, minus 6. Now if I multiply this by minus 2, I'm going to get minus 2 minus 10, positive 12, and add it to the second row, add it to the third row, and I get 0, 0. Now this was minus 10 minus 3, so that's going to be minus 13. So minus 13, and then we're going to 12 plus 14 is equal to 26. Alright, now we have introduced zeros into the lower triangular portion of the matrix. That is the first step of Gaussian elimination. So we have accomplished the first step of Gaussian elimination. Okay. The next step, that first step, by the way, is called forward elimination. Okay. Forward elimination. That's the technical name. Okay. So forward elimination is the process of introducing these zeros to the lower triangular portion of the matrix. Now, once we have this, we have one equation right here, this very last third equation, minus 13, 26. That represents an equation. I've got minus 13x3 equals 26. This is one equation with one unknown that we can just solve for algebraically, which if we do that, we get x3 is equal to 26 divided by minus 13, which comes out to be minus 2, right? Alright, so we know x3. So now that we know x3, we can back substitute that value for x3 into this second equation, which if we write out, we now have x2 plus 5 times x3 is equal to minus 6. Well, substituting in our value for x3, we get x2 minus 10 equals minus 6. Well, we do the algebra and we get x2 equals 10 minus 6, which is 4. Okay, now we have x3 and x2. We can substitute them back up into this final equation and get our solution for x1, which if we do that, we have the equation x1 plus x2 plus x3 equals 3. While substituting in our values for x2 and x3, we get x1 plus 4 minus 2 equals 3. So these combine to be 2, and then we subtract 2 from both sides, and we get x1 equals 1. There. That is the second step of Gaussian elimination, called backward substitution. So Gaussian elimination has two steps. So let's talk about this. So Gaussian elimination has two steps. First step, step 1, is called forward elimination. And that amounts to introducing zeros. Introducing zeros in the lower triangular portion of the matrix, portion of the A matrix. Okay, so that's the first step. And then once we do that, we do, so this is step one. Let's make this cleaner. Step two is backward substitution. And that consists of solving for the last unknown using the last equation, then back substituting this answer to get the other unknowns, Alright, so those are the two steps of Gaussian elimination. Now what about Gauss-Jordan elimination? So let me come back up here to our matrix. So what Gauss-Jordan elimination does, and it's just kind of an extension of plain old Gaussian elimination. Instead of stopping here where we've got the zeros introduced in the bottom, what I can do is I could multiply this second row right here, this second row again, by some constant value, and then introduce a 0 here. And then I could multiply this third row by some constant value and add it to this row right here to get a 0 here. And then I can also multiply this third row by a constant to introduce a 0 here. And so now I'll have zeros everywhere except for the main diagonal. And then I can scale each equation, the first equation, the second equation, and the third equation, so that there's only ones on the diagonal. So when I do that, I essentially have the identity matrix here, and my solution appears in this right-hand column. So this column right here, solution. So if you wrote out the equations, you would literally have 0 times x1, 1 times x1. If you wrote out the equations, let's just do it down here. Give ourselves some more room. So if our system looks like this because we've introduced zeros in the other locations, then our solution actually is going to show up here, which, what was our solution again? Let's see, it was x1 was equal to 1, so 1, 4, minus 2. So we get 1, 4, minus 2. That's what it would look like in the end when we were done with Gaussian elimination, with Gauss-Jordan elimination. And when you write that in equation form, it looks like x1 plus 0 times x2 plus 0 times x3 is equal to 1. which that simplifies to just x1 equals 1, and then you get 0 times x1 plus x2 plus 0 times x3 equals 4. That simplifies to x2 equals 4. Then you got 0 times x1 plus 0 times x2 plus x3 is equal to minus 2, which simplifies to x3 equals minus 2. So there you go. You just get the solution for when you use Gauss-Jordan elimination. So the question is, why would you want to use Gauss-Jordan elimination instead of Gaussian elimination? Well, Gauss-Jordan elimination just takes a lot more steps and is actually less efficient when you implement it on a computer. It's faster just to do forward elimination and the backward substitution on a computer. So in another video, I'm going to go ahead and explain how we would try and implement Gaussian elimination on a computer. So forward elimination followed by backward substitution. And before I kind of close that, though, I want to highlight one issue here, and that is, what if our equations were slightly different? So let's say I had the linear system of equations, and just like the other ones, but instead of having a 1 here, so 0, 1, 1, 2, 3, 7, 1, 3, minus 2. This is the exact same matrix that we started out with, except for I put a 0 here instead of a 1. Okay, so x1, x2, x3. Okay, equal to our B matrix, which was 3, 0, 17. Okay, so now I've changed the first equation. So now when we try and do Gaussian elimination, we actually can't use this first row to introduce zeros to the second row and the third row because there's a 0 here. So what do? Well, the answer is simple. It's called pivoting, and later when I talk about the actual computer algorithm, we'll learn that these diagonal elements are called the pivots of the matrix, and when you have a 0 there, you have to do this technique that's called pivoting, and that's where we actually swap one row with the other. So we could fix this by pivoting, and when we pivot, what we do is we just swap rows. So I could swap this with the second row, and then the second row with the third row, and I get this. So 2, 3, 7, 1, 3, minus 2, 0, 1, 1. And I still have x1, x2, x3. And that's now equal to, B vector also has to change. This is now 0, 17, and 3. So typically when we pivot, we always try and make sure that the largest coefficient in the column shows up at the top. And there's a reason for that, and when we implement it in a computer algorithm, computer program, that I'm not going to explain here. But now that we've pivoted our equations by swapping rows, we can go ahead and proceed like we normally would with Gaussian elimination. Okay. So when we implement a computer program that doesn't use pivoting, so we just proceed without even trying to check if we need to pivot. That's called naive Gauss elimination. When we introduce pivoting, we call it Gaussian elimination with partial pivoting. Okay, partial pivoting because we're actually, you can do a full pivoting, which is where instead of just swapping rows, we also consider swapping columns in the matrices. That would be full pivoting. But when we just do partial pivoting, we just talk about swapping rows, and that tends to be enough. It's efficient. It's the most efficient kind of elimination method, Gaussian elimination method. And full pivoting is more expensive to do on a computer than just partial pivoting. It makes the algorithms a lot more complex. So in another video, I'm going to talk about how we can develop an algorithm for Gaussian elimination, naive Gaussian elimination, and how to kind of get started programming that in MATLAB. So we'll see you in the next video.